Hi viewers, welcome to LMS Solution. Today we are going to see about grid connected solar PV system with the battery energy storage. So this is one single line diagram of grid connected solar PV system with the battery energy storage. So it consists of solar panel and is connected to the DC bus via boost converter. So this will be act as a DC bus, this line, and then it has battery storage. So the battery storage connected to the DC bus via bidirectional converter, and the DC bus has some DC load, and also this system going to be connected to the single phase grid via bidirectional DC to AC converter or bidirectional converter. So here we are going to create some logic, that means for sending power from solar PV with the batteries to grid, and also purchase the power from the grid to the solar PV with a battery system, right? So for that we created some logic. That logic nothing but that means we have to take the power of PV and then state of charge of battery. So power of PV, and then we have to take SOC of the battery. So these two parameters going to be compared with some predefined value. That means this power of PV is less than 100 watts, and then SOC of the battery is less than 10 percentage. Then the reference current given to that this bidirectional converter is negative. Okay, so you have to provide negative reference current. So that means we have to purchase the power from the grid, not to charge the battery. So you have to get the power from the grid, not to charge the battery, as well as to power the DC load when there is no power in the solar panel and the SOC of the battery is less than 10 percentage. If suppose the PV having the maximum power, so excess power, that means so it can supply power to the DC load as well as charge the battery. Apart from it has excess power, then the solar PV system can supply the power to the grid. Okay, during that time the solar can supply the power to the grid. So during that time we have to provide positive reference current to supply the power to the grid. Okay, so this will be happen during solar PV have excess power. Okay, and also so whenever the irradiation change in the system environment, right, during that time definitely there is change in the solar power, right? During that time battery going to be supply the power to the DC load as well as supply the power to the grid. So this is a concept we are going to implement in the MATLAB. So let's start with that MATLAB implementation. Yeah, this is the model we created for that grid connected solar PV system with the battery energy storage system. Okay, so here you can see that we are using 8 to 50 watts panel, right? That means here you can see that the panel will be connected in series. So each panel rating is 250, and total power it can generate maximum at the standard test conditions around 2000 watts. Okay, and then here you can see that so this is a voltage at maximum power point for single panel, and then current at maximum power point for a single panel, right? So we are using 8 panel, right? Then it can supply maximum, that means it will generate the maximum voltage of uh, around 240 volt, right? So next you have to see the PV and IV characteristics of this solar PV system. So here just you have to click this option array at a 25 degrees Celsius, and then you can fix the different irradiation level, right? And then you can see the after clicking that plot, right, you will see the IV and PV characteristics of the consider solar array, right? So it has 8 series model. So here this is known as PV characteristics of that consider a solar panel. So this is the IV characteristics of the consider solar array, right? So here you can see that for 1000 watts per meter square, right? The maximum power is around 2002 watts, right? So when irradiation is reduced to 800, so that maximum power is around 1599. For 600 watts per meter square is around 1197, and then for 400 watts is around 799.91. Okay, for 100 watts per meter square the power is around 187.8. Okay, so this is a variation of peak power of the solar panel with respect to change in the radiation. Okay, so the solar power receive two inputs. So one is temperature, another one is radiation. So we have created two scenarios. So one is for a static irradiation condition, another one is dynamic irradiation condition. So you can use both condition in this system. Okay, so the solar PV is connected with the DC bus. So this is going to act as a DC bus. Okay, so it's going to be connected with the DC bus via boost converter. Okay, this is nothing but boost converter, and then in DC bus we connected one DC load. That means resistive load is connected in the DC bus. So next one is the battery. So here, so the detail of battery. So we are using 12 volt with the 20 series battery. Okay, then voltage, nominal voltage around 240 volt. The capacity of the battery is around 48 Ah, and then initial state of charge is fixed at 50. Okay, so this is a battery detail of the simulation, and then it's going to be connected with the DC bus, right, via this bidirectional converter. So next, and then the DC bus is going to be connected to the grid, right? So this is a grid, single phase grid. So grid, this is a detail of grid. The grid detail is 230 volt with the 50 Hz frequency. Okay, it's connected to the grid is going to connect it to the DC bus via this LC filter and then single phase inverter. So for solar PV system, we are going to apply incremental conductance MPPT to extract the maximum power from the PV panel. So the detail is available here. Here you can see that we are going to measure the voltage and current of the PV panel, and it's going to be given to the input for that MPPT algorithm, incremental conductance MPPT, and then it will generate duty cycle. So this duty cycle going to be processed via PWM generator, and it will be generate the pulse. Okay, this pulse going to be control the IGBT of this boost converter. Okay, in order to extract the maximum power from that solar PV array, it's based upon irradiation and temperature. Okay, and then to control this battery and bidirectional converter, so we are going to use the voltage controller for bidirectional DC-DC converter, because here the bus voltage is maintained around 400 volt. So the input voltage for this and input voltage in the battery is 240 volt, and here also this battery, that means solar panel voltage is around 38, and then so voltage is around 240, right? So here we are going to choose the bus voltage is around 400 because it going to be connected to the single phase grid. So we need to maintain the bus voltage is around 400, so it can uh, nominal voltage used for connecting with the single phase grid. So our aim is here we need to we are here we need to maintain voltage at 400 in the DC bus. So here we are going to apply voltage control bar for that bidirectional DC converter. So we are going to measure the voltage from this bus. Okay, so this bus voltage, actual bus voltage, compared with the reference, and it process via PA controller, right? So based upon this error signal, right, reference voltage and actual voltage from the bus, the PA controller will generate the controlling signal, or it generate a duty cycle. This duty cycle is going to be processed via that PWM generator. It will generate the pulse. So this pulse will control the IGBT used in the bidirectional converter. Okay, so it going to be control this switch in order to maintain the bus voltage is around 400 volt. Okay, so next you have to see about inverter control. So this is a single phase inverter, so it's connected to the DC bus. Okay, so here we are going to apply that current control method. So for that we are going to measure the inverter current, so output of inverter current. Okay, so this actual current is going to be considered it is the actual current from that inverter output. Okay, so here we are going to apply current control. So in current control we need to generate current reference. So in order to generate current reference, we are using some logic here, right? So based upon PV current and SOC, so already told that if PV power is less than 100 watts and then SOS is less than 10 percentage, then I reference equal to minus minus, okay, it will take minus value. So here we fixed it minus 10. So minus 10 means the grid going to be supply the power to the this DC microgrid. Okay, so when the SOC and IPV is greater than 100 watts and greater than 10 percentage, okay, then the reference we are setting here is 2. Okay, that means it receive the power from the DC microgrid to AC. Okay, it take the power from the DC microgrid. So this is the logic implemented in this part. So after that, here we are going to apply unbalanced DQ frame, right? So for that we have to generate that DQ reference, that means D and Q reference current, right? So here we are going to convert that the inverter current into D reference Q reference by means of this AB to TQ conversion. Okay, after that it going to be compared with the actual current. That means this is actual current is taken from that grid, that means inverter. So this actual is going to be converted into DQ by means of AB to DQ conversion. So this DQ is actual current quantity in DQ frame. So this DQ going to be compared with this D reference Q reference, right? So here we are using current PA controller. So this current PA controller will generate the controlled output. Okay, so this control output once again going to be converted into AB quantity. Okay, so here we are using DQ to AB conversion. So after conversion of DQ to AP conversion, so we will take only A quantity for generating the pulse for that single phase inverter. So this A quantity can be processed via PWM generator. Okay, so it's a controlled voltage generate from that current controller of inverter is processed via PWM generator. It generate the 4 pulse. Okay, so this pulse going to be trigger the IGBT of this inverter in order to change the power from grid to DC microgrid and DC microgrid to AC grid. Okay, so this is a concept of implementation of that control algorithm for connected solar PV system. So next I am going to simulate this model with the two kind of option. So initially that battery SOC is maintained at 50. Okay, so now I am going to simulate this model. So this is a PV measurement. So this is battery measurement, and then this is a DC load measurement, and then this is SOC of the battery, and then this is inverter voltage and current grid current measurement. Okay. Now you can see that initially the irradiation set at 1000 watts per meter square. So the maximum power is extracted around 2000 watts here, right? So during that time, the PV going to be supply this DC load. So you can see that DC bus voltage. So the DC bus voltage maintained at 400 volt, and it supply that means the PV is supplying the power to the DC load. The DC load power is around 1000 watts. Okay, the remaining power will be shared with the battery. So here you can see the battery current is around uh, nearly 2 amps, right? Minus 2 amps. Minus 2 amps means battery in charging mode. So you can see that SOC of the battery is increasing now. So and then the same the 2000 watts, right, is the remaining 1000 watts shared by battery as well as this grid. Okay, so now we can see that the irradiation changed to 500 watts per meter square. Because of changing irradiation, what happened, the PV power goes to around 1000 watts, right? But the DC grid, right, should supply the DC load as well as AC grid. Okay, so because of this change in irradiation, what happened to the battery? Now you can see that so battery change direction. That means charging mode to discharging mode, right? So that means the current is goes from negative to positive, right? So now you can see that the SOC of the battery, you can see that is decreasing. That means battery in a discharging mode. So you can see that the DC load receive the power as well as AC load also receive the power here, right? So next we go for another scenario after 0.6. Okay. So here you can see now after 0.6 what happened, the irradiation goes to nearly 10 watts per meter square, right? So that means the power goes to 0, right? So because of PV power goes to 0, so battery is charging with the higher current, right? Sorry, discharging at the higher current. So initially it discharged at 2 amps, nearly 1.5 amps. Now it discharging at around 5 amps. Okay, because battery only supplying the power to the DC load as well as grid. Okay, so now you can see that the logic from that system here. The reference current is now set at 2 amps peak. Okay, now I will zoom that inverter current, you will get the idea. So now you can see that 2 amps peak current will is supplied to the grid. Okay, so here also you can see that, so 2 amps current is flowing into the grid. Okay, so now that DC microgrid supply the DC load. Okay, it supply the DC load as well as grid. Okay, next you have to see the changes after point 0.9, right? After point 0.9, what happened? The irradiation changed to 10 watts per meter square to 500 watts per meter square. So we will check the response. So what happened with this system? Now we can see that the PV power is increases to 1000 watts. Okay, because irradiation changed from 10 watts per meter square to 500 watts per meter square, then it will be maintained at 1000 watts per meter square. So because of that, you can see the battery charging current, right? It sorry, battery discharging current is changed from 5 amps to nearly 1.5 amps. Okay, so now PV as well as battery supply the DC load as well as grid. Okay, during this condition. So next we see the another condition, that means irradiation change from 500 to 1000 watts per meter square. So what will be happen to the system? Okay, now you can see that after 1.2 second, the irradiation change from 500 to 1000 watts per meter square. Because of that, what happened to the PV power? The PV power is increasing now. Okay, after some time you going to be settled at 2000 watts. So because of increasing PV power, so what happened to that battery current? Battery current goes to negative. Okay, that means battery change the mode from charging to, so sorry, discharging to charging mode. Okay, and also you can see that now also DC receive the power as well as grid also receive the power. Okay, so now you can see that SOC of the battery is increasing now. So this is known as power balance in the DC bus. So it indicate the PV current, PV converter current. So this uh, brown color indicate the DC load current, and then red color indicate the battery converter current. So this is inverter input current. Okay, so this is final sum of this all current, right? Algebraic sum. So here you can see that power balance, that means current balance is equal to 0 in the DC bus, right? So always equal to 0. Okay, so power balance is maintained in the DC microgrid. Okay, so this is the first scenario. Okay, so next you have to discuss on another scenario. That means suppose I'm going to fix the battery percentage less than 10%. For example, I'm going to fix 9.998. Okay, next we have to see the response of the system. The radiation is maintained at the same, initially is at 1000 watts per meter square. After 0.2 or 0.3 second, it changes to 500. So every 0.3 second, the value of irradiation is keep on reducing. After that, it keep on increasing with some value, right? So now the SOC, you can first you check the SOC. SOC is keep on increasing because so solar PV have power, right? Solar PV have power. So solar PV supply the charge the battery as well as supply the load as well as supply the grid. Okay. Here you can see that here the 2 amps peak current will be as reference, right? So solar PV now supplying the power to the charge the battery, supply the load, DC load, and then supply the grid. Okay. So here you can see that the SOC of the battery is increasing. Okay. So after 0.3 second, what will be happen? That means the irradiation change from 1000 watts per meter square to 500 watts per meter square. So because of definitely there is drop in power in the PV. So that means is around it going to be maintained around 1000 watts. Okay. So because of reduction in the PV power, so what happened to the battery? Battery changed from charging mode to discharging mode, right? Now battery balance the power to the DC load as well as grid along with the PV power. So here you can see that battery goes to discharging mode. PV power is reduced because of that reduction in the irradiation. Same time you can see that bus voltage maintained at 400. DC load receive the power and then grid also receive the power. Okay. So after 0.6 second, right, the PV, that means irradiation of the PV panel is changed to nearly 10 watts per meter square. Because of that, PV bar goes to 0 watts, right? So what happened during that time? You will check that one. During that time, so condition that means PV have that does not have any power. So battery SOC is less than 10 percentage. Then grid need to supply the power to the charge the battery as well as power to the DC load. Okay. So we will check the condition. Yeah. Now we can see that PV power goes to 0 and also SOC is less than 10 percentage. So what will be happen? The logic will be changed to minus 10, right? If now the reference current is minus 10 amps peak. So now we can see that the grid now supplying the power to the DC microgrid. So because of this, okay. So because of this, so what will be happen? The battery going to be charging mode, right? It's changed from discharging mode to charging mode, okay. And also DC load receive the power, right? So I will zoom that current, you will get some idea. So here that phase sequence of that grid going to be changed, okay, reverse, right? And also the reference current minus 10 amps, right? Minus 10 amps is supplied from that grid to charge the battery as well as to drive the DC load. Now we can see that SOC of the battery is keep on increasing because of power from the grid. So we'll wait after 0.9. So after 0.9 irradiation one sign change from 10 watts per meter square to 500 watts per meter square. So what will be happen because of that? We'll check that one. So once again, so here you can see that because of change in irradiation from 10 watts per meter square to 500 watts per meter square, the PV power is settled around 1000 watts, but the condition not is satisfied. So that when we created condition, the both condition is true, then the current reference will be changed, right? So only one condition is is true, right? That means the PV power is more than 100 watts, right? So, but that SOC of the battery is still less than 10 percentage. So then it receive the power from the grid, right? So now the system operate in grid that means the power the DC microgrid receive the power from grid. PV also supply the power. Okay, so both the PV power and grid power going to be charge the battery. Because of that, what will happen? The charging current of the battery is increased from minus 1.5 amps to minus 6 amps, and also it receive the DC load also receive the power from the grid. Okay, now you can see that next after 1.2 second the irradiation change from 500 watts per meter square to 1000 watts per meter square. Because of that, PV power increase from 1000 watts to 2000 watts. So because of that, what happened in the battery charging current is increases from minus 6 amps to minus 10 amps. Okay, so still grid supplying the power, because the PV power is only greater than 100 watts. So only one condition is true. So it's not true for SOC of the battery. Now we can see that if SOC is goes to greater than 10 percentage, right? So now what will happen? The both condition is true. So that the reference current change to 2 amps per 2 amps peak, right? So now you can see that now the DC microgrid supply the power to the AC grid, right? That means PV supply the power to the battery to charge the battery, and also it provide the power to the DC load, and also it provide the power to the AC grid. Okay, just you see that. So after changing of that condition, so once again PV is extract the maximum power around 2000 watts. Because of that, it charge the battery as well as it supply the power to the DC load, and also it supply the power to the grid. Okay, now we can zoom this one. So now you can see that the phase sequence now reversed. So AC grid receive the power from the solar PV with the battery energy storage system. So this is the working of this model. Thanks for watching our videos. Kindly subscribe our channel and also click bell icon about notification about upcoming video. Okay, so you can download MATLAB file, that means MATLAB application file from following website. So this is a official website for that YouTube channel and LMS solution, right? So you can go to this website and click download MATLAB file. So you can have different kind of MATLAB projects, right? So you can download from this website. And another announcement, we are conducting two workshop on June 13 on June 13. Okay, about wind energy powered EV charging station. So this is MATLAB workshop, and also we have we plan to conduct another workshop on PET controller for DC-DC converter on June 20, 2021, right? So if you're interested in the workshop, you can register. Okay, thank you once again.